Hi there, we're going to talk about periodic trends or trends of the periodic table. And there's several of them today. So we'll talk about those, see if we can't organize the elements, but there's a few things we have to handle first. We need to go back and talk about the valence electrons and the octet rule. And the octet rule is that atoms are going to gain, lose, or share valence electrons in order to get that full outer energy level of 8 electrons. So that they'll be very stable like the noble gases. Since noble gases already have that full octet, they are very stable. So they're very unreactive. They don't react very much at all. They already have their octet, so they don't have to. Other elements are going to react in order to get their complete octet. They're going to lose, gain, or share electrons to get that full set of 8. When you're looking at the periodic table, got my big one here. Okay, so we look at the periodic table. Nonmetals are going to be over here. So nonmetals are close to 8. Everything in group 5 has 5 valence electrons. That's close to 8. Everything in group 6 has 6 electrons. That's close to 8. So what these nonmetals are going to tend to do is they're going to tend to gain electrons. So they'll have a negative charge here. It might be easier to see my awesome periodic table here. So everything over here has a negative charge, which you probably can't see because it's really small. Everything in group 5 has a -3 charge because it gains 3 electrons. Group 6 has 6 valence electrons, so they're going to gain 2 electrons to have the 8. And all the halogens will gain 1 valence electron in order to have their octet. They already have 7, they just need 1 extra. Okay, so they're going to gain in order to fill their octet. But the metals over here, most of the periodic table is metals, the metals are going to lose valence electrons. So they'll have a positive charge. Everything in group 1 has 1 valence electron. It's easier, what these atoms are going to want to do is whatever requires the least amount of effort, the least energy. So it's easier for everything in group 1, they have 1 valence electron, it's easier for them to give up that 1 valence electron because underneath the next lower energy level will have a full set of 8 valence electrons, or 8 electrons. So they'll have their octet if they give away the 1 valence electron. Well, everything in group 2 has 2 valence electrons, so they'll want to give away 2 electrons in order to get their octet. Now, valence electrons and the charges that they're gaining, the number of electrons they're gaining and losing, vary. Okay, most metals, they're going to gain electrons. Most nonmetals will lose electrons. So which electrons are valence electrons? Well, those are the ones in the outer energy level. If you're looking at the electron configuration, the superscripted number, here you see it as the 2 and the 6, those are the valence electrons. Those are the ones that are considered the valence electrons. So that's how you can tell, if you're looking at electron configuration, what the valence electrons are. This is the reason that we've been having you draw your Lewis structures the way that you have, because in the first, that s orbital, 2 electrons go in there, then they start filling up the p orbital. So we have you draw your first 2 electrons together, the 1 and the 2, representing the 1 and the 2 that would go in the s orbital, and then the rest of them go 3 goes there, 4 goes there, 5 goes there, then we start all over. 6 goes there, 7 there, 8 there. So you fill up those orbitals before you can double up the orbitals. So this orbital notation correctly represents the valence electrons of which group? We'll look at the number of electrons. There's 1, 2, 3 electrons. What group has 3 electrons? Group 13. Which one does this represent? 1, 2, 3, 4, 5, 6, 7. What group has 7 valence electrons? It's group 17, the halogens. Okay, complete the orbital notation for the valence electrons for the alkaline earth metals. So what would that be? If it's an alkaline earth metal, which group is that? Well, it's group 2. So those 2 electrons are both going to go in that s orbital. Okay? So some trends that we're going to talk about atomic and ionic radius, ionization energy, electronegativity, and one that's not listed on here, Columbic Attraction. Okay, first, atomic radius. It's just exactly what it sounds like. Atomic radius is the size of an atom. It's the from the middle or the nucleus to the outer edge of that electron cloud, to the outer edge. It's the radius from the center to the outside edge. It's the distance between an atom's nucleus and its valence electron. Okay, atomic radius increases toward francium. So when you're looking at the periodic table, get this one here, it's kind of bigger. When you're looking at the periodic table, atomic radius increases going this way and it increases going this way. Why? Well, as you move down the energy levels here, what's happening as I move down the column? Well, it's adding another energy level on top. Okay, so there's one energy level here, 2 energy levels, 3 energy levels. It's kind of like putting on a sweater or putting on a shirt, then you put on a long sleeve shirt, then you put on a hoodie, then you put on a coat. You're making yourself bigger and bigger and bigger because you're adding layers. So that's why atomic radius increases this way. And it also increases from left to right. Oop, hang on, somebody's at the door. Okay, thanks for your patience. Okay, atomic radius increases from left to right, or from right to left on the periodic table. Increases toward francium. I'm looking backwards. Increases toward francium. The reason the atomic radius increases as you move this way is because everything in this group has 1 valence electron, way out in the furthest away energy level. Over here, these atoms will have 7 valence electrons. Okay? There's a greater attractive force here than over here. Okay? More electrons are being pulled in tighter by that positive nucleus. Over here, they're not, that 1 valence electron not being pulled in as tight. There's not as many protons either. Okay? Protons increase as you go this way. That's the atomic number. Increases as you go this direction. More protons in the nucleus makes it a stronger magnet, if you will. So that positive charge in the center of the atom is pulling in tighter on those valence electrons, causing the atomic radius to be smaller over here, larger over here. But what you need to remember is atomic radius increases this direction. Okay? There we go. That's a picture of some of the atomic radii. Gives you a good idea of what they look like. The vertical pattern, so I've explained as you go down, it gets larger because we're adding extra energy levels. The horizontal, this way, atoms get larger as you move left. So as you move from the alkali metals toward halogens, they get larger. Elements in the same period have the same number of energy levels, but remember I said they have a larger number of protons. Okay, makes it a stronger magnet. Fewer protons means electrons are held loosely. So francium's 1 valence electron wouldn't be held as tight. It would be way far out there in that 7th energy level. More protons means that those electrons are going to be held tighter, okay, making it a smaller atom. Okay, so if we were going to put these in order of increasing atomic radius, okay, we've got some really nice pictures here. It's kind of obvious. So increasing, so that means from smallest to largest. So the smallest would be beryllium. Next would be magnesium, then calcium, and strontium. Okay, it follows the trend. Okay, here's beryllium. Beryllium, there's magnesium, calcium, and strontium. Remember that as you go down, the atomic radius increases. So all you would need to do is look at that periodic table to know that. Okay, how about this one? Silicon, phosphorus, aluminum, and sulfur. Okay, remember atomic radius gets bigger as you move from right to left. So it would be sulfur, phosphorus, silicon, and aluminum. Let's check me, see if I'm right. Yup, I figured. All right, so ionic radius. Ionic radius is similar to atomic radius. Atomic radius is the size of an atom. Ionic radius is the size of an ion. Remember that an ion is an atom that has lost or gained electrons. So it follows the same basic trend, meaning increase, increase. Okay, same direction as atomic radius. But I kind of want to let you know what an ionic radius means for the ion versus the parent atom. Cations. Cations are positive ions. The way I know that it's a positive ion, if you look right here, cations has that T in the middle, looks just like a plus. Also, I've heard it say that cations are positive. Cats, pause. Yeah, pretty funny. I make all kinds of chemistry jokes. So cations are positive ions. So that means it would be a metal, like magnesium. Magnesium with a +2 charge means that magnesium has lost 2 electrons. If it loses 2 electrons, that means it's going to be smaller than its parent magnesium atom. Okay? They're always smaller. Cations are always smaller than the neutral atoms. Magnesium +2 is smaller than magnesium because it's lost 2 electrons. So on the opposite side, for those nonmetals or the anions are negative ions. So really only one way that I can think of to remember that. I had a kid one time tell me that anion reminds them of the word onion, and they don't like onions, so onions are negative for them. So that's one way to remember that one. So anions are negative ions, like the nitrogen with a -3 charge. Okay, since it has 3 extra electrons, it's going to be bigger than its parent atom of nitrogen. They're always larger than their neutral atoms because the ion has more electrons. All right. Ionization energy, it's the amount of attraction that an atom has for its own electrons. Okay, think of it as the energy required to remove an electron from an atom. All right, think about it for a second. So think about fluorine here. Okay, fluorine has 7 valence electrons. Its 7 valence electrons are pretty close to the nucleus. If I were going to draw the Bohr model for fluorine, would look like that. So what do you think? If it's got 7 valence electrons and they're held pretty tightly to that nucleus, it requires a lot of energy to pull those off of fluorine. Okay, what about, let's say, sodium? So sodium would look like this. So there's sodium. So you see, sodium has 1 little valence electron. It's easier to pull off 1 valence electron that's a little further away from the nucleus than it is to pull off 1 from fluorine, because fluorine's almost got 8. It does not want to give any up. It's very hard to remove electrons from fluorine. Okay, so a metal like sodium is happy to give away its 1 electron or 2 or 3 because it doesn't require a lot of energy to do that. Nonmetals want to gain electrons, so it takes a lot of energy to pull electrons from that. Hope that makes sense. So ionization energy, I always say if it has an E, it increases toward helium. Helium, E. Okay, so it increases toward helium. Ionization energy increases as you move this direction. Okay, you see increasing ionization energy here. Helium is the smallest atom, but it has, here, I'll draw in a different color. Helium has just 2 valence electrons right here, down here. But it's full. Remember, helium only has the 1 little s sublevel. How many electrons can fit in the s sublevel? 2. It has 2. And they're slam on top of the nucleus. Okay, right up next to it, close as they can be. The atom with the highest ionization energy is helium, little bitty helium, because it's so hard to pull this octet of 2 electrons away from helium because they're so close to the nucleus. So I say if it has an E in it, it increases toward helium. Atomic radius does not have an E anywhere, so it increases the opposite direction. Okay, it increases as you go up the group because the electrons get closer to the nucleus, so higher ionization energy. It increases as you move to the right because there's more protons pulling in on those little electrons. So let's see if we can't put these in order of increasing ionization energy. Let me find the periodic table for you. Okay, there we go. There. Okay, so we've got silicon, tin, lead, and germanium. So silicon, tin, lead, and germanium. They're all in the same group. So we're going to put them in order of increasing atomic ionization energy. Ionization energy, and remember, if it's increasing, it means it's going from the least ionization energy to the greatest. So we said that ionization energy increases that way, so that means as you go up a group, ionization energy will increase. So, lead, tin, germanium, silicon. Let's see if I'm right. Yep, I was right. How about this one? Carbon, nitrogen, what else? Boron and oxygen. Okay, ionization energy increases that direction. So that means if I'm moving this direction, ionization energy increases. So boron, carbon, nitrogen, oxygen would have the greatest ionization energy. Yep, told you. Okay, electronegativity. Electronegativity is the ability to attract electrons in a chemical bond. Now, we've talked about ionization energy, which is attraction of attraction for electrons that an atom, for its own electrons. Electronegativity is the attraction for electrons when it bonds to something else, okay? It's the ability to attract electrons in a chemical bond. And some atoms have a greater attraction for electrons than others. Okay, think of it as a measure of how badly an atom wants an additional electron. Well, hopefully that gets you to thinking right now. Elements that are nonmetals on this side of the periodic table, on the right side of the periodic table, they're close to 8. Okay, they want another electron really bad. So electronegativity is going to increase that direction. And remember what I told you, if it has an E, it increases toward helium. So that means electronegativity is going to increase going this direction. Okay, it's going to increase toward fluorine, right there. Fluorine has the highest electronegativity. Now look over here, you see the nonmetals? Everything else has a number, and that's the electronegativity value in Paulings, which we'll talk about that later. But the noble gases don't. Why do the noble gases not have electronegativity values? Well, think about what does electronegativity mean. That means it is the attraction that an atom has for the electrons when it's bonded to something else. Noble gases don't bond to anything else. That's why they have no electronegativity value. So you see here, fluorine has the highest electronegativity. Noble gases have 0 for electronegativity. Down here on the other side of the periodic table is the least amount, is the least attraction for electrons when they're bonded. But fluorine has the highest electronegativity. Fluorine's the most electronegative element. It almost has 8 valence electrons, and it really wants one more, really close to the nucleus too. If you offer it one electron, it will greedily rip it away from you. Fluorine atoms will violently take electrons away from atoms that are around them. Fluorine's very dangerous to work with. We have a really cool video, so I'm going to show you this neat video.
Well, the reason that fluorine makes such strong bonds is because it is a small atom, and the nucleus is relatively highly charged because it's right on the right-hand side of the periodic table, but the electrons don't shield this nucleus, so it is very so-called electronegative. It attracts electrons to itself from other elements.
I've changed the prop now for some just normal barbecue briquettes. So this is pure carbon.
So we haven't done anything. This is cold charcoal and cold gas. And the gas just touching it is enough to start the fire. Think of that. Just the cold gas setting things on fire. Most chemists are really too frightened to work with fluorine. You can't use it in glass vessels. It doesn't attack glass, but if the glass is a tiny bit wet, and most glass has moisture absorbed to it, then the fluorine forms hydrogen fluoride when it reacts with the water, and the hydrogen fluoride just eats through the glass.
Kind of neat, huh? Fluorine's very, very reactive. Noble gases will have virtually no electronegativity, again, because they don't bond with anything. So let's put these in order of increasing electronegativity. Okay, if electronegativity increases toward helium, except for helium doesn't count because it's a noble gas, but it increases that direction, which one of these would have the least electronegativity? So we've got iron, cobalt, krypton, nickel, and manganese. Okay, so which has the least electronegativity? Right, it's a noble gas. Krypton has the least electronegativity, so that would be first, okay, followed by manganese, iron, cobalt, and nickel. See? We did it. Okay, how about the next one? There's sulfur, tellurium right there, selenium, neon, and oxygen. That's tougher because we're going this way and they're kind of all spread out. Okay, but let's see, sulfur, oxygen. Neon definitely would have the least electronegativity because it's a noble gas, so we know that goes first. And whatever's furthest away from fluorine would have the next lowest electronegativity value, which would be tellurium, I believe, then selenium, and sulfur, and oxygen. Yep. Okay, Columbic attraction is the force of attraction between the positive charge of the nucleus of an atom and the negative charge of its electrons. Okay, so it's the charge, it's the attractive force between the positive nucleus and negative electrons. Okay, positive nucleus and negative electrons. Two things affect Columbic attraction. Thing number one is distance between the negatives and the positives. There's an indirect relationship between the force of attraction and the square of the distance. What this basically means is that the distance between the nucleus, as the distance from here to here increases, the Columbic attraction decreases. Why? Because it's not close anymore. It's like a magnet. If you pull a magnet, if you put two magnets together, you know how you were kids and you started playing with magnets and you notice that if you push them together a certain way, they'll snap together. Okay, they're attracted to one another. Okay, if you pull them just a little bit apart, then they'll still be attracted. You can still feel that pull. But what happens when you pull them way apart? You can't feel the pull anymore. Same thing here. The further away the negative electron is from the nucleus, the less the Columbic attraction, okay, the lower that attractive force. As the distance between the nucleus and the electrons decrease, so I have my eraser. So if I have electrons here, and that's S energy level, that Columbic attraction would be higher. Why? Because they're closer to the nucleus. They're closer. You're putting those magnets, okay? You're putting them closer and closer and closer, and all of a sudden you have a real strong attraction and you can feel it and they pop together, okay? That's the same thing. It's the way that works with the negatively charged particles and that positive nucleus. Okay, that's one thing that affects Columbic attraction. Another thing that affects Columbic attraction is the strength of the charged particles. So what that means is if I have an atom with a greater number of protons, that's going to have a higher Columbic attraction. So let me see. Let me pick a couple. Let me do over here. Pick a couple. Let's say magnesium and chlorine. Okay, so magnesium has 12 protons, okay, and it has electrons. Chlorine has 17, I can't draw, 17 protons in its nucleus. Okay, I drew. And got electrons around here. Which one of those do you think would have a stronger Columbic attraction? That one. Oh, I'm sorry, that one. I'm looking backwards. That one would have a stronger Columbic attraction because it has more protons. Okay, stronger magnet in the middle, pulling in tighter on those electrons. All right, so the distance between the charged particles and the strength of the charged particles, meaning whether it has more or fewer protons, will increase or decrease the Columbic attraction. That's what affects Columbic attraction. So that's all for today, but that's probably all you can handle today. Sometimes the brain gets mushy. So go eat a bowl of Cheerios and relax.